In this screencast, we'll be discussing Gauss's law, and I'll do an example for you of a charged sphere, the field inside and outside a charged sphere. Gauss's law, as you'll find, is a nice way. It's much, much easier than using Coulomb's law. In cases of symmetry, where you have some idea of the direction of the electric field, you can apply Gauss's law. These cases are spherical symmetry, cylindrical symmetry of a long cylinder. It either needs to be very long or approximately infinitely long. So infinitely long cylinders, spherical shells, volumes, spheres of volume charges, and infinite planes. So it doesn't work in every case. It kind of has a small subset, and you need a little bit to know where the field is going. However, you'll find it's much, much easier than Coulomb's law. This is the differential form. What we're going to do first of all is we're going to integrate both sides at respect to volume. So let's take the integral of the left-hand side. And remember, Griffiths' convention is to use d tau. We'll do the same thing over on the right-hand side. All right. On the right-hand side here, this is basically, if you recall from the earlier screencast on Coulomb's law, this is just charge. We need to be careful of what kind of charge it is. So first I'm going to write this down as 1 over E naught, and we're going to qualify what kind of charge this is. I'm just going to call it Q, but we're going to put a subscript there. That's important. From the divergence theorem, what we know is that del dot E up above here, this is the same thing as the flux through the surface that encloses that divergence. Okay, so E dot dA, the flux through the closed surface, is equal to the total charge enclosed by that surface over E naught. All right, remember the divergence theorem basically says that the sum of the faucets, this is what Griffiths says, I like this one, the sum of the faucets is equal to flow out through the surface. So if you want to find out the flux through a surface, you can either sum up the divergence of all the sources, that's one way to do it, or maybe you could somehow intercept all the field and add up the flux. What's nice is that Gauss's law here in its integral form is basically saying that the flux through the surface, and the surface is one that you're going to draw, we'll see, the flux through a surface is equal to the charge enclosed by that surface. All right, that kind of makes sense. Griffiths goes into some depth about field line picture and how you can see it's actually by just drawing field lines and enclosing the surface of the field lines, and that basically has something to do with the charge, right? So the flux through the surface has something to do with the charge that created that field. Let's look into this in more detail by doing a problem. So what I've drawn for you here is, or what it's supposed to represent anyway, is this is a solid charged sphere. All right, and the charge density is constant, and I'm interested in the electric field at point P. This sphere has a radius of A, and so let's write down Gauss's law in the form that we're going to use. It's going to be the integral form. Once again, that is going to be the flux through a Gaussian surface, which we have yet to draw, is going to be equal to the charge enclosed by that surface over our factor E naught. So probably the first thing we want to do here is draw a Gaussian surface. I'm going to draw it in a different color here. Let's draw it in red. So in order for this to be meaningful, I actually want my Gaussian surface to, I want P to be on the boundary of that surface. All right. And I'm going to draw a sphere. That's supposed to be a sphere. All right, this is a spherical shell. So we're drawing it in 2D here, but imagine that that dashed line wraps around this solid sphere that's in green. And here's what I'm going to assume, or here's what I need to assume, is that the direction of my E field and the direction of the surface I draw are parallel. All right, so we need to know something about the electric field before we even start. And in this case, for the sphere, I'm assuming that my electric field at P is going to be in the radial direction. Therefore, I'm going to draw a surface that is going to have a unit vector a normal vector in that same direction. All right, so if I draw a sphere, if I draw a spherical shell, the normal vector is in the r hat direction, and I'm assuming that my E field is in the r hat direction. All right, that's quite a bit of assumption. So we need to know the direction of the E field, and we need to draw our surface accordingly. I could draw my surface however I want, but then I'm going to have trouble doing the... I could draw a crazy surface, but if I want to extract the E field out of this, which I'm going to show you, I need to draw a surface that makes sense. So now what I can do, this is a slight cheat, because we have to know, again, the direction before we start. But now what I'm going to say is that E is going to be equal to the charge enclosed. Let's fix that there. It's going to be equal to the charge enclosed over E naught. And you know, why don't I change colors here? Divided by dA. And then let's actually make this general. Even though we're doing a specific problem here, it's going to be in the direction that is the normal vector to the surface. Okay, so everything I've drawn in red has to do with my Gaussian surface. So this is the area integral of my Gaussian surface, and this is the normal vector to my Gaussian surface, which is going to be parallel to the field. All right, so there's a bit of assumption there. I need to know, in my special case with my sphere, I'm assuming the E is going to be in the r hat direction, and dA is going to be in the r hat direction. So let's determine what the integral of our Gaussian surface is. Let's do this part first. All right, so this is just going to be the surface integral of the area element of a spherical shell, which in our case, we forgot to do one thing. So what is the radius of our spherical Gaussian surface? We're going to call it R. Draw a little nicer R here. It's R. It's not A. So this is a thing that often students will mix these problems up. We have A is the radius of our volume distribution, but R is the radius of the Gaussian distribution. All right. I want to leave it R general because maybe I'm in the future interested in the point P out here, not right here, and all I need to do is increase the R of my spherical shell. That's my Gaussian surface. All right. The area element in spherical coordinates is going to be, in this case, r squared, and we're not integrating over r, and it's going to be sine theta d theta d phi. And then the limits of integration go 0 to pi for theta, and 0 to, let's make that 0 a little better, 0 to 2 pi for d phi. Zero to 2 pi. All right, and one of the ways to check your work to see if you're correct here is this thing. It's the surface area of a sphere, which should be 4 pi r squared. And in fact, the integral of sine theta d phi, given these limits, this part here gives the solid angle 4 pi. All right, so let's write that down. Let's move this over to the side. I hope it's attached. That's all right. This is just going to be equal to four pi r squared. All right, and again, we need to be very careful that it's not 4 pi a squared. It is the surface area of our Gaussian surface that we drew, not the surface area of the volume distribution. All right, we're almost there. All we need to do, well, we already said that n hat, we can write that n hat in this case as r hat. So maybe we'll write that down here. N hat is equal to r hat. We had to know that in a sense before we even started the problem. And now let's finally find Q inc. Q inc we can do a few ways. In this case, we might just say that the total charge enclosed, or the total charge on this distribution is Q total. And it just so happens that my Gaussian distribution encloses the entire distribution. So what we can do in this case is we say that Q inc is equal to Q total. Now there's some more information on my problem. Sometimes people don't do that, but if I know that that whole spherical volume charge has a total charge Q total, look, I've enclosed it all, and I can just say Q total done. All right, another way though to get Q inc, I can say that this is equal to the volume integral of the density of the distribution here. So this one of what is enclosed by my Gaussian surface. Okay, so Q inc in this case, and only this case because we're enclosing the entire distribution, can we say it's Q total. In general, what we need to say is it's the volume charge density integrated over the volume where there's charge distribution. So in this case, what I do is I would integrate, if I want to do this format, what I do is I would integrate over here. I could keep integrating all the way out to my surface, but guess what? There's no charge in between the green and the dashed line. So in the case, for this case here, this is just going to be rho, and it's going to be the triple integral now again in spherical coordinates. Why don't we just write it down? I was going to skip it, but all right, it's going to be 0 to A. Why A? Because there's no charge outside of A. Really, we go all the way to out to R. But guess what? There is no charge between radius A and radius R. So actually, all the there's no density there. The density is 0 there. And then once again, 0 to pi. Whoop. And then 0 to 2 pi. A little bit messy there, but I think you get the point. And then this will be R squared sine theta dr d theta d phi. If you want, we can keep that prime notation like we did before. I didn't do it above. In this case, we're not too worried about mixing. So here, unlike Coulomb's law, we don't really worry about prime. The density, but again, look, it was constant, so I could take it out. If it's not constant, I need to leave it in and integrate. All right? So let's actually finish that integral. Maybe I can make this smaller. Hopefully this one's not connected. Good, it's not connected. That's all right. Let's make this a little bit smaller. All right. What this is equal to is going to be rho 4/3 pi a cubed. All right. So what we can put on the top here of our expression, right, this is our expression for the E field using Gauss's law, is for sure what I'm going to put down on the bottom is 4 pi r squared. And for sure what I'm going to put here is n hat. Q inc, we get a choice. We could just put Q total. That's nice and easy. Or we could put rho 4/3 pi a cubed. Either one will give us the answer. Let's write that down on the next page, on the next screen. So in the case that R is greater than A, E is going to be equal to Q total. That's what the total charge enclosed by my Gaussian surface is, divided by 4 pi E naught R squared. That comes from the bottom over here. And then the direction is R hat. All right, and that is for R greater than A. Cool. We could also, if we wanted to, we could write it like this. We could say that's the same thing as rho 4/3 pi a cubed, right? That's another way of writing the total charge enclosed by my surface is either Q total, I just named it Q total, I said, oh, that's all the charge there is, or it's the surface charge density times 4/3 pi a cubed. And this is because the surface charge density, sorry, not the surface, the volume charge density is constant. And then just divided by the same thing. 4 pi E naught r squared r hat. So those are two ways of writing the same thing. I have to admit, I kind of like this easy one, the simpler one. And one of the reasons is because, look, this is just the E field for a point charge. And so what this is saying is that even though this is a larger, not a point charge, it's a big spherical volume charge, the field outside of it is just like a point charge, where instead of little q for the point charge, it's the entire charge in that distribution. All right, let's do this again, and let's do it for the inside. Let's just recap real quickly. So this is really a generic. You can use this for every Gauss's law problem right here. Okay, so what's up here you can use for everyone, that the E field is equal to the q enclosed by the Gaussian surface, and then the direction of the vector of this E field is going to be the normal to that surface that you draw, and that and then this is the area of that surface, and E naught. All right, one thing that's very important is, check it out, because of the symmetry here, our surface had to be, we couldn't just draw any surface, right? All around it has to be a sphere. The E field needs to be the same along the surface I draw. All right, that's a qualification of this surface. I couldn't draw like some wiggly thing and make this work. The E field all along the surface, or the E field all along the surface, needs to be the same strength, right? So do we agree that if I take the E field here and here, the same radius around, it's going to be the same strength? That's the only way I can undot this, right? That's where we're kind of cheating, is we're taking this vector and we're turning it into multiplication and sticking the vector component on the other side. We can only do that if E is constant along the surface that we choose, right? And then the surface must be, the normal vector to the surface must be the same all along that surface as well. Okay, what if now I'm actually interested in the electric field inside this spherical charge, this solid sphere? Once again, we need to draw a distribution, and we're going to draw our distribution cleverly, or sorry, not our distribution, our Gaussian surface. And here's what I need to know again. I need to know that the E field that I'm going to find out is going to be the same, right, along this, on the edge of the surface. And I also need to know that the E field is going to be parallel to the normal vector on the surface, and that way I can undot this thing. All right, so we're just going to do the same approach again. Let's do we know again that n, this is our assumption, is going to be equal to r hat in this case. We know that also that the integral of the surface I drew, we need to actually draw a radius again. So again, I'm going to call it r, because once again, maybe I'll be interested in the future, not at a point here, but a point closer in, and all I have to do is shrink that spherical surface by reducing the radius. All right, so the integral of my my element is going to be the same as it was last time. It's going to be 4 pi r squared. All right, because my surface, the shape of my surface stayed the same. I just shrunk the radius down. So what's changing in this problem is actually the charge that's enclosed. All right, and that's what makes this part of the problem different. Is my charge enclosed is different. Let's write that one. So Q inc now for this surface is going to be, we can pull the density out. In general, it's this. Let's write down the general one again. In general, it's the integral of the density summed up over the volume. And again, this is now of the enclosed charge. So again, I want to sum up the volume of my surface. Now, what my surface is enclosed is not the whole volume. All right, and so for our case, density is constant. How nice. And I'm going to skip a step here. D tau is going to be, it's going to be r squared sine theta d phi. And the limits here, the limits of r volume are going to go from 0 to r, 0 to pi, 0 to 2 pi. All right, so this thing here is going to equal to 4/3 pi r cubed, not a. That's important, right? So I'm going to beat a dead horse here, but I'm interested in the charge enclosed. It's the charge enclosed by this surface, which is a spherical shell. All right, and so the charge enclosed by that surface is packed into this sphere, this volume of charge that's only this big, not this big. So the radius is smaller. It's not a 4/3 pi a cubed. It's a 4/3 pi r cubed. It depends on how large my Gaussian surface is now. Okay, we can do one other thing here. Well, let's plug it in, and then I'll show you one other small trick that sometimes we like to do. So E then is going to be equal to, oh, I forgot a row over here. You see where I forgot my row? It's 4/3 pi r cubed times rho. Okay, E then is going to be equal to rho, let's make a little better 4 there, rho 4/3 pi r cubed divided by 4 pi, oh, come on, you can do it, there we go, 4 pi E naught r squared, and that's going to be in the r hat direction. And that's it, that's our answer. Let's simplify it a little bit, and then I'll show you one other way to simplify it to get it in terms of Q total. Alright, the 4's are going to cancel, right, up in the 4's here are going to cancel. We're going to get the 3 on the bottom. The pi's are going to cancel. The r's are going to cancel, some of the r's. And so what we're going to be left with here is it's going to be rho over 3 E naught r hat. Okay? And that is a legitimate answer. We're going to, again, just manipulate it slightly. Look at the form of r in this case. The last one, we were outside, when p was outside the sphere, it went like 1 over r squared. But when we're inside the sphere, it goes like r. It increases linearly until we get to the edge. The field at the center would be 0, right? And then as I go out, it gets stronger and stronger and stronger and stronger. Oh, and then suddenly it gets weaker and weaker and weaker and weaker and weaker as I go away. All right, let's rewrite this one other way on the next slide. This is fine. This is the answer, so this is inside the sphere. Let me write that down too. So this is for r less than a. All right, just one last little thing to make it match the other one in terms of Q total. So I wanted to show you one last little step that's not necessary, but it's nice to get this E field inside the sphere now in a similar format, at least in terms of Q total. So it matches the one that's outside the sphere. So let's do this. Rho, which is constant for us, is going to be Q total over the total volume of the distribution, right? Q total describes this entire charged sphere. And so if I wanted the charge density, which is constant, it will be the entire charge over the entire volume. So that will be 4/3 pi a cubed. Let's see, get rid of that stray mark there. That looks good. All right, now let's plug that into our equation. So for inside the sphere, that's going to look like Q total times r, it's still linear in r hat over 4 pi E naught a cubed. All right, and once again, this is for r less than a. Okay, that's it. So what we should see is that as we look at the electric field from the center, it starts at 0, it increases linearly, and when it gets to the edge, it starts to fall off as a 1 over r squared. And the field on the edge here of the distribution should be equal. That's it. More fun Gauss's law to come, cylinders and planes. Enjoy. Gauss's law is fun. It actually is pretty fun, but once again, it's a little silly because we need to know a lot about the E field before we start, and you can only use it for certain distributions.